and for this you have to be aware of a bit of probabilities, such as we'd start with the concept of probabilities. That independent event is anything such as a trial, like flip of a coin or throw of a die, or happening of rain, or like chances of an accident. Everything that we have, that I mentioned in the last minute, are called events. Now independent event is that is not affected by any other event. For example, flipping of a fair coin twice. Now when you flip a coin twice, what happens is that when you flip a coin, this event of flipping a coin twice is an independent. These two events are independent events. Now comes the concept of dependent events. Now dependent events, if we draw a card from, like, even if drawing the cards can be made an independent event, but over here we would draw two cards one by one with replacement, and that makes them dependent events. Why? I show you. When we draw a card, and at that point of time the deck has 52 cards, and when we pick a second card, now the deck has 51 cards. So when we draw two cards one by one without replacement, we are changing the state of the bag or the deck of cards from which we are drawing, and the two events become dependent on each other. The draw of second card becomes dependent on the first event. Now the addition rule of probability says that PA or B means that either event A happens or B happens, such as throw of a fair coin. In the flip of a fair coin, if you get heads or if you get tails. Now if you are not bothered about a head or tail, then the probability that whether you get a head or whether you get a tail is 1, and that can be represented as probability of heads plus probability of tails minus probability of heads and tails both. Now heads and tails both would never come, as the two events probability of heads and tails is independent. But otherwise, if you have dependent events, if A and B are dependent and you want to find the probability of A or B, it can be written as PA plus PB, probability of event A plus probability of event B, minus probability of A intersection B, which is this area. Now, multiplication rule, you have to remember it in the form of intersection. PA intersection B is equal to PA multiplied by PB. This line over here, vertical line, is termed as given. PA intersection B is PA multiplied by PB given A, or it is also equal to PB multiplied by P A given B. Now we move on to the next slide. Bayes theorem. It says that P C given A is equals to PA given C multiplied by PC divided by PA. Now you must be realizing over here that you can derive Bayes theorem from the multiplication rule itself. It's like just simply a rearrangement of these two, this equation. And one other representation, when we call for when we use Bayes theorem in for the application of classification, we have to remember that posterior is equal to likelihood multiplied by prior given divided by evidence. PA is evidence over here, PC given evidence, so A is evidence here. Now the problem of fruit problem. If we have this data where we are given that we have banana, orange, or some other fruit, and we know about the characteristics of these fruits, such as long, not long, sweet, not sweet, yellow, not yellow. and we have to find out that we are given some information about, and we are just given some fruit, and we are told that the fruit is long, sweet, and yellow. Now we have to find out, we have to answer the question if it is a banana, or is it an orange, or is it some different fruit. Now the way we do it is that we find out some probabilities that we have to figure out before getting into the actual solving the actual problem of finding what is the proof that it is banana. And I write it down for you. The thing that we have to find out is this: p banana, given that it is long, sweet, and yellow. And we have to also find out p orange, given long, sweet, yellow. And once we know these two probabilities, we would the answer would be whichever probability is higher, whichever is higher. And now, so the way to answer this p banana, given that p long uh, p long sweet and yellow, how do we expand this? Using the Bayes equation. And the Bayes equation tells us that this is equal to p long, p sweet, p yellow, given banana, divided by p of long, sweet, yellow. Now, similarly, we would have to do it for the p orange, where the equation would be similar, except for in place of banana, we would be having p banana. Now, if we know that long, sweet, and yellow are independent events, we can again expand this equation to this way. One second. Is equal to, I'd write it down, the long, sweet, yellow, given b is equal to b, that it is long, sweet, yellow, and banana also, divided by p banana. Now, in this way, now if we want to find out, now if we now when we say naive Bayes, this implies that all the events are independent of each other. Events L, S, Y, such as L, S. So L is for long, S is for sweet, and Y is for yellow, and B represents our banana. Now, if we are dealing with all the events such as are independent, and in this case, this implies that P, L, S, Y, and B is equal to PL, PB, no, one second, PS, PY, PB. Now, once you have understood this part till here, then it is easy for you to figure out how to solve the fruit problem. And we would do it in the next slide. So just as we see over here, we have to find out all of the individual probabilities. And in the next slide, we are doing just that. We try to figure out what P banana is. P banana is 40. No. P banana is out of total 50 are banana, 30 are orange, 20 are other. So 0.5, 50 by 100. P orange is 30 by 100. P other fruit is 20 by 100. Now P long is 50, not long is again 50. Now P long is 50 by total 100. P sweet is 65 by 100. P yellow is 80 by 100. 0.8. Now when we put all of these into this equation, we would get P banana given PLSY equals to PLSY given B times B over PLSY. Now over here, as you can see, if we know P long given banana, P long given banana is this equation over here has been derived from Bayes rule and Bayes theorem. Now we have to put the values. P long given, we derived it over here also. Over here in this slide. So P banana given long, sweet and yellow is equals to P long given banana, which essentially means that, one second, which essentially means that it is a banana and we have to find out the probability that it is long. So banana long not long is 40 by 50. 40 by 50 is 0.8. P sweet given banana is 35 by 50, which is 0.7. And P yellow given banana is P yellow given banana is 45 by 50. And P evidence. So I think there is a mistake in this slide over here. This is okay. Okay, P yellow given banana is 0.9 and P banana is 0.5. So this comes out to be 0.252 given the denominator. Now, if we want to find out P orange given long, sweet, yellow is equal to is 0. Why? Because one of the probabilities is 0. P long given orange is 0. Because of this number over here, P orange given long, sweet and yellow is 0. Now what is the probability that it is other fruit given long, sweet and yellow? Then we have to again use the same equation such as we derived over here. And because we know that we know that the probabilities are independent, so we use this equation: P long given other fruit, P sweet given other fruit, P other fruit, P yellow given other fruit, and P other fruit divided by P long, sweet and yellow. Now P long given other fruit, we would again use these equations, these numbers from this table, and fill them over here, and we would get this number. And then we would compare the probabilities of P banana given the specifics and P other given the specifics, P orange given the specifics, whichever one is higher, we would simply answer. Now, the Naïve Bayes classifier for spam and ham. Now, if we have training data of this sort, where we are given that document D1 is good, document D2 is very good, and document D3 is bad, document D4 is very bad, and document D5 is very bad, very bad. Now, if we are given the test document D6, which says good, question mark, bad, and very bad, we have to read this training data and then predict if this document D6, which is our test data, is a ham or a spam. Now, spam mail is, you are aware that anything that you didn't ask for is but pushed into your mailbox is spam, but ham is the good mail. Ham is the good mail. Now, again, we would see that similar kind of equations that we saw in our previous slide. If we again try to write the equations for well, if what we have to predict is, what we have to predict over here is p ham given d6 and p spam given d6. Now, essentially what d6 is equal to, d6 is nothing but your words good, bad, and very bad. D6 is nothing but your good, bad, very, and bad again. One second. Contains good one time. Well, I think we should just D6 is here this. Very bad. Now, if we go for checking what is P ham given good, bad, very, bad is equal to, now I'd refer to the equation I have in this slide. P 1 second. P good, bad, very. This is using the Bayes rule, comma, ham divided by P good, bad, very, bad. I just extend it a bit more like this. So this is so this is from Bayes equation, and once we, so to derive this P good, bad, very, we would say that these are independent events, right? So P good, bad, very, bad, ham. Because the problem is of naive Bayes, we'd assume that all the probabilities are independent probabilities, and to do that we would have to, as we are seeing over here, P d6 P ham given d6 intersection of this, and when we try to find the intersection of these, and we know that these are independent probabilities, so this is roughly equal to P ham times P good, not P ham, P good given ham, p bad given ham times p very given ham times p bad given ham times ham times p ham. Now you can calculate these probabilities uh, from these equations from by calculating by using these, like for example, I'd explain one thing. P ham is two males of ham and 3 males of spam. So 2 divided by 2 plus 3.4. P spam is equals to 3 males of spam, 3 over here, 2 for ham, 2 for ham, 3 for spam, and 0.6. Now, Laplace smoothing says that when Laplace smoothing is that whenever you are counting any term in your document, you would add 1 to it. For example, if, for example, number of times vary appears in your ham males is 1, but for along with 1 you would also add one more. Now if you would add 1 to every time vary appears, it would become 1. And in the denominator also, p vary given ham is p vary divided by all the times the other terms appear in the ham document. So p vary again, p vary given ham again, p good given ham, like it appears 2 times, but we would add 1. Now number of times term bad appears in ham males is 0, but we would add 1. Now why do we do Laplace smoothing? Because at times if we try to find the probability that p bad given that it's ham, that would be 0, and we cannot accept that because it will affect our final calculations if 0 appears too many times. Now, the way we calculated the number of terms, the probability p vary given ham, we would again do it for good. P number of times good appears for ham is 2. So we fill in 2 here plus 1 divided by vary in ham. That is 1. Good 2 times plus 1, 3. And then for bad 0 plus 1 for Laplace smoothing, and this becomes 0.5. Similarly for bad is 0, but the denominator remains the same. Now we would come to spam mails. Now spam mails are no different. You only have to repeat the process which we did for ham. I'll make it explain it for bad. Probability p bad given spam, such as number of times bad appears in spam mails is 1, 2, 3, 4. But for Laplace smoothing we add 4 plus 1, and then number of times the other terms appear, that means 3, because probability p bad given spam is number of times term bad appears and number of times the other terms appear. So it's like number of times vary appears is 1, 2, 3. 3 plus 1, 4. Number of times good appears, good doesn't appear with spam mails, so 0 plus 1, 1. Number of times bad appears in spam mails, 1, 2, 3, 4. So 4, and this gives us 5. Now this is 0.5. Now if we look at, now we use these probabilities again. Now p d6 given ham is equals to p good, p bad, p good, bad, very bad, and ham all together divided by p ham. Now p good, bad, very bad, ham is equals to p ham multiplied by p good given ham, p bad given ham, p very given ham, and p multiplied by p bad very ham. Now if we put it in the equations. Now we are not considering denominator here. Denominator is your p ham, and we replace this term with this term. If we divide p, if we put all of these terms over here in place of this, we put this, p ham will get cancelled, and what we are left with is p good given ham, p good given ham, p bad given ham, p very given ham, and p bad given ham. which we can figure out from our previous calculations. And PD6 given ham we can easily figure out. Now P ham given D6 is equals to PD6 given ham multiplied by P ham divided by PD6. Now the denominator term PD6 comes in both the terms, and we would ignore them, and we would only calculate the numerator, and which is over here is, and then based on our numerator we classify them as P, it is spam. Any questions? Any questions?